we have understood nitriding, we have seen gas nitriding, we have seen iron nitriding. There is another method which is available with us is liquid nitriding. Liquid nitriding is done at temperatures between 510 to 565. The case hardening medium is molten nitrogen bearing fused salt, both containing cyanides and cyanides. Liquid nitriding is subcritical case hardening process, thus processing of finished parts is possible because dimensional stability can be maintained. Again, it is done at lower temperature as we are doing gas nitriding. Also, liquid nitriding adds more nitrogen and less carbon to ferrous product. More nitrogen is going. But what we are interested in is more nitrogen and less carbon. Sursulf solutions are available which are patented by German people. And Tuftride is patented by German and Sursulf is patented by French people. These two solutions, powders are available in the market. And then like salt bath, let it be oil fired or electrical fired or gas fired. You melt it, put the components, you can do quenching or air quenching depending upon your composition of steel. The liquid nitriding processes has several proprietary modifications and is applied to a wide variety of carbon low alloy tool steels. It is used to improve the wear resistance of surfaces and to increase endurance limit in fatigue. Hero Honda motorcycle crankshaft used to do earlier liquid nitriding earlier. Now they have shifted to induction hardening. Now we are coming to induction hardening. Induction hardening is applicable to wide variety of heat treating operations. This includes surface hardening and tempering. You can do hardening and tempering with induction. Basic theory includes an induction heating circuit is fundamentally a transformer wherein the inductor carrying the alternative current is primary and the material to be heated is made secondary by merely placing into it within the confines of the loop formed by the inductor. Next. Application to industrial hardening, crankshafts, all Leland crankshafts, Telco crankshafts at Pune who are doing induction hardening, camshafts in machine tool, transmission shaft, induction hardening, bar stock, gears on very big scale induction hardening is done. Very high rapid production rate, more motorcycles, more cars, more trucks, more tempos, more tractors are coming. And induction hardening, the advantage of electricity is very basic. The electricity you need not to stock. You do not need any room to stock the electricity. Electricity you can use as and when, whatever you want you can use. More you use, more you have to spend. Less you use, less you have to spend. So electricity is very good raw material which cannot be seen. No storage place, no drums, no gas, nothing is required. So induction hardening all over the world is working wonderful results, and people who are manufacturing induction furnaces are really doing very good thing financially, and they are on the top grade in the management. Next. Now we have come to the last where we should all be happy. Thank you very much for your excellent cooperation. Now we can go for question answer session. We have, I think, finished within 45 minutes. Mr. Abba? Yes, we have finished. If any question answers are there. Martin side is very hard. So whatever higher hardness jobs are there, they are more brittle. Yes. Right? So whether you are looking for more hardness or you are looking for more ductility, or you want combination of both, that is what you say. If you want less hardness, benign. If you want higher hardness, Martin.
Today's Martin side structures are heavily used.
What people are using, do not worry. People will be doing annealing, people will be doing normalizing. In annealing, we have got different processes. Subcritical annealing is there, full annealing is there, interstitial annealing is there. In normalizing also, whatever your structure you are looking for, accordingly the heat treatment cycle should be set. So we cannot say benite is better. For Mr. Prem Arora, benite may be better because he is looking for hardness between 45 to 50. Okay? For me, benite is not useful. I want 65 as that. So for me, Martin side is required. So whenever you are quenching the steel, suppose you have got 62 RCR and you want 58 to 60, you have to temper to 180 degrees. Suppose you want hardness between 45 to 52, you will temper the same steel to 280. Suppose you want hardness 28 to 32, the drawing indicates 28 to 32, you have to temper that steel to maybe 600 degrees. So it all depends what hardness you are looking for, what hardness the drawing has defined, your design engineer is defined. Yes. This is the chart. On left hand side we have got Vickers hardness tester. Second row we have got Brinell hardness number. Right hand side we have got Rockwell hardness number. Then we have got Shore hardness number. And then we are indicating the tensile strength. Higher the hardness, higher the tensile strength. Tensile strength, first chart it is indicating in tons per square inch. On right hand side it is kilogram per square millimeter. So what is the tensile strength you are looking for will be decided by your hardness. If you want very high tensile strength, higher hardness is required. If you want low, suppose you are looking for say 84 tons per square inch tensile strength, your hardness will be coming 41 RC. If you are looking for say 120 tons per square inch, this is not correct, this 28 should be read as 58, should be 58. Suppose you are looking for say 51 tons per square inch, your hardness, Rockwell hardness should be 22. So hardness and tensile strength, they are related with each other. Like when you are going to doctor, the doctor is checking blood pressure, the equipment is fitted here, but actually he is checking how your heart is functioning. So hardness, when we are indicating, we have in mind tensile strength. Are you getting?
Yeah.
And where are the skills? So whether Benite is better, Benite can be better for Mr. Prem Arora, Martensite can be better. For that gentleman, ferrite will be required, because if he is in automobile industry, whatever sheet metal is there should not have any hardness, it should have very good ductility. For if they are manufacturing axles, 1040 steel, they will be looking for 50 RC. If I am doing gas nitrating, I will be looking for 70 RC. So my structure will be different. Yes, any other question? Unimex? One more point I would like to add here. See, whatever drawings we have shown you here, like 0.8% TTT diagram we have shown, it is only for that particular steel. That will not be applicable to alloy steel or stainless steel or high speed steel. Like that, we have more than 1 lakh steel grades available today. More than 1 lakh. People are being patented also. So everything will have different diagram. For that, ASM volume is there. Different diagrams. Even iron carbon diagram, whatever we have shown you, is the simplest form of iron carbon diagram we have shown you. If allying elements are added, maybe A1 will either go down or will go up. 0.8 will come maybe to 0.4. Are you getting? These are the basic fundamentals, and different steels are there. More than 1 lakh steels are there. And every steel will have different TTT diagram, different iron carbon diagram, depending upon the alloy elements. Why we have only taken iron carbon diagram for our understanding. Iron carbon diagram also, all temperatures will change. If nickel is added, boron is added, chromium is added. Yes sir, any other question from backside? Pune people, any question in your mind? We can share with each other. Or Mr. Prem has suggested, if you have any questions, you can write.
For 0.2 carbon content, how much hardness will be? You have told that 45 RC will get. But as such, I don't have any example in my company that if for 0.2 carbon content we have reached for 45 to 50.
What is the diameter of the copper?
That's not diameter, because that see, my material is EN8, right? EN8 flat, 80 by 80, around 550 to 560 length. I'm not getting.
Hey, क्या अपना TTT diagram क्या? TTT diagram. TTT diagram. Now there are two things we should keep in mind. One is hardenability, ability of the hardness, ability of the steel to get hardness. Number one. And second, the quenching. Now we will come to this diagram, TTT diagram.
I've got EN9 material which contain 0.38 to 0.2 carbon.
No, EN8 is 0.3, 0.35 to 0.5. Right.
But I'm not still getting the hardness up to 45.
45 RC you are not getting.
Yeah.
Maybe there is some problem with the
What
hardenability.
can be upon the material?
No, material, there is nothing wrong in the material. There is only the problem in the hardness procedure, what is the equipment procedure.
See, this is a carbon content on left hand side, on right hand side we got hardness. If your steel is SA 1040, EN8 you said, 0.4% carbon, it is bound to get anywhere hardness between 55 to 58.
Yeah. The maximum it can achieve up to 58. 58
Right?
or maybe 60 also.
Now, suppose you are not getting that hardness. What?
Carbon.
No. I will answer in a proper way so that you understand. Because you have to feel that answer. See, if you are not getting this hardness, the second question apply hai kya? TTT diagram kya? The second thing is you have to see which diameter of the job you are doing. Are you getting?
Yeah.
Suppose your EN8 shaft is only 25 millimeter diameter. Arbitrary set we are talking. We are just talking from understanding point of view. You will get this hardness. Suppose that instead of 25 millimeter, suppose your diameter is 250. Are you getting me?
Yeah.
Then you will not get carbon content to gap. Carbon content gap. You will not get even say 30 RCs. Because iron carbon hai gap, TTT gap. Because this austenite, when you are quenching, it should not touch this nose. So this is known as critical quenching rate. So right from austenite, as I told you, that carbon atoms whatever are available in FCC, you should not allow them to go out. So you have to quench it immediately. 880 or 840 degrees centigrade, as the operator has taken out, you have to just quench in water immediately. Now what is happening when you have got 25 millimeter diameter, this critical cooling rate is possible. But when you have got 250 millimeter diameter, we are just giving example. See, this critical cooling diameter you are not able to achieve. So how you are cooling is something like this. You are coming in a baryte region. So that steel does not have the required hardenability which you are looking for. Hardenability is the chart card. Now this is say 10 carbon steel. The maximum diameter which you can quench and get hardness up to the core is 1.1 inches. Now it is 13. When you are adding manganese, the hardenability is increasing. So it depends what is the diameter. Are you getting me?
Yeah.
You got it. That critical cooling rate you are not able to achieve if the diameter is more.
Because of the bigger material.
Because of the bigger mass. That critical cooling rate is not coming. It is getting cooled slowly. So either you are forming benite or you are forming ferrite and pearlite, and if it is instantaneous, small diameter, immediately that critical cooling rate is possible. And that is the reason you have to go for alloy steels. Where alloying elements have got better hardenability and your critical cooling rate is very. There are some alloy steels where you need not to quench in water, you need not to quench in oil, you can just do air quenching. Like H grade, just take it to hardening temperature, pull it out, फैन लगा दो उसको, हवा में ठंडा कर दो, उसका हार्डनेस ऑटोमेटिकली आ जाएगा. What is H grade? The guaranteed hardenability. That is why alloy steels are there.